As I discussed in the last lecture with humans, many of our genetic diseases, many of our genetic disorders are recessive. And only when that person, that offspring, is homozygous recessive, both alleles are the recessive, will it show, will it affect the phenotype. But that doesn't mean that just because somebody has the quote-unquote normal phenotype, they developed correctly, doesn't mean they can't be a carrier. Carrier is somebody who is heterozygous. There is a dominant allele there, which means the recessive does not affect the phenotype. The carrier can pass on that, has the potential, the probability of passing on that recessive allele to their offspring. When we look at albino examples in us humans, albinoism is an example of this. Two parents who look normal, have correct pigmentation not only in their skin but in their hair and their eyes, can have an offspring, a child that is albino. When you look at what I'm referring to, two parents, both are carriers. Big A, little a. Little a means the recessive albinoism allele. Their potential for every one of their offspring, it's a 3-to-1 chance. 3 chances, or 3 out of 4, 75%, however you want to think about it, 3/4 chance that their offspring is going to be normal pigmentation. 1 in 4, or 25% chance that their offspring will be albino. Also means that it's a 50-50 chance that two parents that are carriers for the albino allele will have a child that is also a carrier. Please keep in mind, when you look at this Punnett square here of 4 blocks, 3-to-1 chance for normal versus an albino child. That does not mean that they have 4 children, the first one, boom, the next 3 are going to have be here. This one's now taken. No, it means for every child, for every offspring, each child, each offspring gets their own Punnett square. Okay? I bring this up because previous years, students seem to think, if they have 4 children, 3 are going to be normal and at least one of them has to be albino. No. Each child is its own probabilities. Individually. Probabilities are low, but it could be that 2 parents that are carriers can have 4 children that are normal. It's low probability, but it's a chance. Just like it's a chance that the 2 parents who appear normal but are carriers could have 4 children that are all albino. For an offspring to have disease that is caused by a rare or a recessive allele, this is rare. It's more common out there for there to be people that are carriers. Carriers for this recessive allele, which is a recessive trait, which could be considered a recessive disease. This is why in farming they try to track who and what is mated with whom and what so that they can try to weed out recessive traits that are either lethal or non-advantageous in us humans. We have basically as a societal taboo incestuous relationships for just this reason. If you're sitting there marrying and mating and having offspring within the same family tree, your gene pool is quite shallow. People who were carriers, you start to increase throughout the generations the probability that instead of being carriers, they are now homozygous for that recessive trait. Saw this a lot in medieval times with in Europe with the royalties, the royals. They like to marry, royal to royal. Turns out they would be, first cousins. And they just kept marrying and marrying and marrying. And before you knew it, 4 or 5 generations later, they, mental retardations, physical developmental issues, and things like that. So they tried to bring in new blood, try to, get something going again. Some examples of these recessive traits, these recessive alleles that can affect the phenotypes. Cystic fibrosis is one. Cystic fibrosis, it's a recessive trait. The gene, CF gene, is responsible for making a sodium pump. If you're ever a little kid, you put salt on a slug, it kills the slug because it breaks down the mucus. Thins out the mucus that's covering it, keeping it wet, thins it out so that it dries out. Kills the slug. Well, the sodium pump pumps the sodium out of the cells into the linings of alveoli or bronchi to thin out the mucus, because the mucus can get thick. Thins it down a bit so that way every time you breathe out, you're pulling up some of that mucus into your throat and you're swallowing it, you just don't even know it. Cystic fibrosis patients, that pump doesn't work, so they don't pump the sodium, their mucus never thins, it's just keeps thickening and thickening and becomes like a sludge in their alveoli. Great breeding ground for different bacteria and things like that. Well, I've been saying sodium, sorry, it's chloride ions. Oops, my bad. Chloride ions build up. So what happens is they literally begin to drown in the mucus. The different bacterial infections there cause an inflammatory response. Fluid builds up. They have to go to the emergency room and they'll stick a vacuum line down in there and they literally just suck out the mucus. This affects from infancy on up through adolescence and into adulthood. Decreased ability to breathe means lower blood oxygen levels, which lower blood oxygen levels is going to affect physical development and mental development, as well as, internal organs can be affected too. Untreated, generally you'll see this results in death by the age of 5. Treatments are going to be different aerosolized as well as pills to help keep the ions flowing so that way the mucus can stay thin. Every so often they're going to have to go to the ER, get the vacuum thing. Most of the CF patients can make it now into their 40s. Sickle cell is another recessive disorder. Sickle cell, as we talked in a previous chapter, is going to be a mutation in the beta subunit of hemoglobin. This is a mutation that's predominant in the African American community as well as Middle Eastern community. Africans, African Americans, Middle Eastern. As you see here, the red blood cells, because of this crystallization, Means that the red blood cells are going to get caught up. Means they're going to be incapable of carrying a lot of oxygen, so lower blood oxygen levels. If somebody is a carrier, they're heterozygous. There are going to be two forms of the beta subunit made. Some of them will form this crystalline structure, but the remaining that are in the correct form will form this free-floating hemoglobin. So carriers can end up with both shapes of red blood cells. And if they're homozygous, the dominant, the normal, quote-unquote normal hemoglobin, it's just going to be the normal red blood cells